So last week we finished up upon Arrhenius theory. Are you all learning about that currently at school? Where's the pace at right now at Sydney, boys? I know you're all in different classes.
Yeah, we just finished exams, so like we haven't had class for 2 weeks. So it's all out. So like the last thing we did was, I think, like start the theories, but we haven't gone into like a great amount of depth into any of them.
Okay, good. You don't need too much depth for these theories. The only two theories you need a lot of depth for is a theory that we just went through, which is Arrhenius theory and Bronsted-Lowry theory. Everything else, the way you need to structure it is you should have pros and cons. That's it. Definition, pros and cons. That's all you need to know for these theories. So Risa, tell me about the first scientist, Lavoisier. What was his theory of acids?
Lavoisier's theory, he defined acids by composition. So through his experiments, his conclusion was that acids have oxygen in it.
Good. Try not to look at your notes. I want you all to be recalling this from your head. So try closing your books in the first 2 minutes just so I see how we're all going with our content, okay? So good. Acids contain oxygen is what I want to hear. The defining based on composition is not part of the definition. It's a pro. So make sure you separate that, okay? What were the cons, Mithilesh, of defining acids as containing oxygen?
I don't know anything yet.
You can derive this from first principles, Mithilesh. So what are some acids that don't contain oxygen?
HCl.
There you go, right? So binary acids, aka acids. So maybe I'll go up to the notes as well, so you're not completely confused. But this is what we went through last lesson. The reason I put a big O next to Lavoisier's name is because that's how I remember his theory. Now, the main con is that binary acids, so any hydrogen combined with a halogen, is not going to contain oxygen, but it will be acidic. The other main issue is that metal oxides and metal carbonates, which contain oxygen, as you can see here, are basic in nature, which is completely contradicting this theory, right? Nonetheless, the one pro is he was the first person to define acids by composition. Make sense? That's all you need to know. This is very low yield. I would say less than 0.5% likelihood will pop up in your exams. Arrhenius and the next theory after that is what's very high yield. So we're going to jump straight to that. Now, Joe, tell us a bit about Humphrey Davy. So what's a definition? What's a pro? What's a con?
Humphrey Davy defined acids as having a hydrogen.
Good.
But yeah, and then the pro of having the pro of it was that he was able to test that because he I think he was the one who combusted.
No, that was Lavoisier. So as you can see up here, Lavoisier has combusted non-metals like sulfur to form sulfur dioxide, and he then dissolves it in water to form acids. Okay. Yeah. Humphrey Davy studied acid-metal reactions, and that's how he came to the conclusion that acids contain hydrogen, because the hydrogen did not come from the metal, so it must have come from the other reagent, which is the acid.
Yeah.
Does that make sense? Now, he was right in his theory. All acids, well, most, you will learn there are exceptions, virtually all acids do contain H. But the issue here is some substances contain hydrogen that are not acidic. And you can see a prime example here. What do we call this substance, CH4? It's a greenhouse gas. Methane. Methane is the gas name. Methyl is when it's a group attached to another bigger compound, but we'll touch upon that in Mod 7. So this is methane, a greenhouse gas. And it contains hydrogen, but it will never release hydrogen ions in solution, which is what Davy's missed, the concept of the hydrogen ion, right? So that's the key con. There are compounds that contain hydrogen that did not behave as acids, methane being a prime example. You don't need to know the scientist. This scientist just further elaborated on Davy's by saying the hydrogen is a replaceable hydrogen, aka this hydrogen can be removed from a substance, and only when the hydrogen can be removed can it behave as an acid. So that was his explanation of why methane is not acidic. Good. This scientist you must know very well. So Riyasat, take it away. What is your definition of an acid or a base? that you've learned so far?
We've learned that acids release or form hydronium ions in solution.
Pause for a moment. Did you know that last year? Did you hear about the hydronium ion last year?
Last year, no.
No. So I want you all to think in year 11, what was the definition of acid you were taught? You may not have been taught acids, but at some point in junior high school, you would have been taught acids.
Yeah.
So,
acids release hydrogen ions in water, and
good.
bases release hydroxide ions.
In aqueous solution.
Aqueous solution, yeah.
Very good. So you're right. When you said in water, that's the exact same as aqueous solution. So good job. So that's your definition of acids and bases. Now, there were three main pros that if you forget a single one of them, you will lose a mark in your exams. What were the three main pros of this Arrhenius theory of acids and bases? There's a reason you were taught this all the way until year 11, because it explains the vast majority of acid-base reactions. So Mithilesh, tell me a bit about pH. What is pH measuring? What is the formula? And what ion is it a function of? Kind of written it all over here.
pH is like it's measuring the amount of hydrogen ions in the solution.
Good.
Yeah,
Okay.
you have the formula there, so I'm not
Good.
gonna say I knew it. I didn't know it.
Yeah.
Yeah.
Good.
And what was the last
Now,
question?
I have a question for you. Is
Yeah.
pH to do with concentration or is it to do with the strength of an acid? So if I tell you there is an acid, X, that contains a pH of 1, is it concentrated or is it a strong acid?
pH of 1 is a strong acid.
Gerald, what do you think?
Yeah, strong acid.
Riaside?
Yeah, it can be a strong acid, but it can also be highly concentrated. Doesn't
Okay,
pH.
I agree most with Riasat, and my answer is that concentration and strength are two completely independent terms. Okay, concentration is just how many moles per liter of HA do you have in solution. Okay, now the way we measure concentration is we can measure pH. pH will tell you the concentration of an acid, right? Because it tells you the moles per liter of hydrogen ions. Strength is completely different. Strength is a function of an acid. If I give you the name of an acid, if I say the word HCl, you will immediately say it is strong. What does it mean to be a strong acid, Gerald?
It displays very strong acidic properties, like it is very bitter. Very
Not quite. You're there in terms of you're describing it, but you haven't explained what a strong acid is. Mithilesh, what is a strong acid?
No, I'm not too sure.
Risa, any ideas?
Have to do with like a portion of, I guess, like how much hydrogen is released. All right, yeah. Okay.
Good. The three words I want you all to write in red pen is ionizes to completion, right? That is the definition of a strong acid. In fact, the definition of strength itself is degree of ionization. Word for word, I want you to imprint that definition in your head. Degree of ionization. So if an acid ionizes 100%, it is a strong acid. Anything less than 100% ionization, it's a weak acid. So in the case of HCl, I think you all know HCl has an irreversible reaction. It only proceeds in the forward direction. So all of the HCl is going to ionize. If there are 100 molecules of HCl, all 100 would form hydrogen ions. Does that make sense? It is a strong acid. But if I gave you acetic acid, for example, which is vinegar, it tastes sour. It's not that strong. It's a very weak acid. You don't get a single directional arrow. You get an equilibrium. All weak acids will form a chemical equilibrium that will obey Le Chatelier's principle. So we'll have CH3, CO minus, and H plus. So key point here is strong acids ionize to completion, have a single arrow, weak acids partially ionize. Now, did I tell you guys anything about concentration here? Did I say that it's a concentrated acid or a dilute acid? No, because HCl can be dilute. If someone makes 0.001 moles per liter of HCl, that is a dilute acid. But nonetheless, it is strong because it ionized to completion. Does that make sense? So my point being, these two terms are independent to one another. You can have a strong acid that is either dilute or concentrated. It just depends on how it was made. Everyone with me? Good. We will explore this further. There's a dot point on this, but it's very important you understand that. pH is all about concentration of hydrogen ions. Good. Now, the reason I brought pH up is the ion that pH is a function of is the hydrogen ion. And who was the first scientist to propose acids release hydrogen ions? Arrhenius. Arrhenius developed the entire pH scale himself. So that is one of the major pros of Arrhenius theory, developed the pH scale. What's another pro? Strength of acids. Do you agree that we explained the strength of an acid based on degree of ionization and release of the hydrogen ion? Right? So again, Arrhenius could explain the differing strengths of acids. He could explain why vinegar was dilute, why hydrochloric acid was strong. And the final benefit of Arrhenius theory, any ideas what it could be?
He explained it in terms of behavior rather than composition.
Yes, that I'd say that's point 4. I'd say you won't lose a mark if you don't say that. The last point is, well, what was a net ionic equation for neutralization? We remember we did that question. There's a reason we did it. What is a net ionic equation of neutralization?
Hydrogen ion plus hydroxide ion gave you water.
There you go, right? So the only way we can explain neutralization, or the first scientist to do so, was Arrhenius. Since acids release hydrogen ions, since bases release hydroxide, the combination of the two is what forms water, right? So the third main benefit of Arrhenius theory is he explained neutralization reactions. So you can't forget those 3 points. So Risa, what was one strength of Arrhenius theory?
It explained the strength of acids.
Good. Mithlesh, what's another pro?
He used the pH scale.
Good. He developed the pH scale. And Joe, final one?
He explained neutralization reaction.
That's it. Everything else is supplementary. Okay, those are the 3 that is a mark I would be looking for. Now, there are equally as many cons as there are pros for Arrhenius theory. Okay, now the main con of Arrhenius theory is the final 2 words of its definition. What were the last 2 words of Arrhenius theory's definition? Aqueous solution. Now, the thing is, you may not know this, but there are acid-base reactions that don't occur in aqueous state. Arrhenius could not explain them at all. And one of the key examples of this is a very high yield reaction, is this one right here. Now I'm going to give you all about 10 seconds to look at this reaction and tell me why Arrhenius can't explain this. So using your Arrhenius theory, what are the issues of this reaction in particular? I'll give you all about 10 seconds to think about that. Okay, so we'll start with Risa. What does this reaction have that a typical neutralization doesn't have? Or the opposite? What's wrong or what's different regarding this reaction versus typical neutralization?
Well, it doesn't form water.
Yeah, there's no water. That's one of the main issues, right? Where's the water? According to Arrhenius, all neutralizations have the same net ionic equation, and there's no water. What's the other issue? Well, we see a hydrogen. Do we see a hydroxide? No. So there is no base according to Arrhenius theory. Yet, when you actually do this experiment, this strong acid will be converted into this slightly acidic salt. Slightly acidic, pretty much neutral, right? So this is a neutralization reaction. We've neutralized a strong acid. Neutralization. So as you can see, there are a couple of flaws which Arrhenius theory could not explain about this reaction. Now, in your exams, they'll give you a practical setup of this experiment and they'll ask you to make logical conclusions. So you'll see that as you do more and more trial papers. This is a very high yield experiment, has its own name called the ammonia dilemma, because this reaction single-handedly led to a new theory in addition to Arrhenius's. Now, everyone, the main issue of this reaction is that it's not occurring in entirely aqueous state. Can you all see that? The ammonia is gaseous, and that is what's complicated this entire reaction. Very good. So the main flaw, this is the first thing you must always say with Arrhenius's theory, number one error, is he did not account for the role of the solvent. Okay? So he assumed that all neutralization, all acid-base occurs in water, but the issue is some substances are acidic in water but neutral in another solution. Arrhenius could not explain that. And that is the one error that you must explain, because the next theory fixes this one error. Good. The next logical issue you can see is sodium oxides and carbonates. Mithilesh, do they have a hydroxide ion attached in their structure?
No.
No. So according to Arrhenius theory, they're not basic. But if you do all the traditional tests, they'll be soapy, they'll be caustic, they can burn, they'll be bitter in taste, so they are basic. Right? And Arrhenius theory could not explain that. The next issue of Arrhenius theory is to do with salts. What did I say about acidic, which is weird. You typically think of salts as neutral, right? Sodium chloride is a neutral table salt. But in reality, some salts can be acidic and some salts can be basic, very slightly. There'll never be strong acids or bases, but there'll be slight or weak acids and bases. And Arrhenius could not explain that as well. So an example of an acidic salt is NH4Cl. An example of a basic salt would be sodium carbonate. That is a salt. Can anyone try explaining why this is acidic or basic according to Arrhenius theory? Impossible. That's why I posited the question. You can't explain it, right? There is no hydroxide here. And this H plus is stuck in the structure of NH4, so it's not going to ionize readily. Good. And finally, there's this word called amphiprotic. Reset, what does protic remind you of? What word does that remind you of?
Protic reminds you of proton.
Good. And what is a proton? What's another name for a proton?
Hydrogen ion.
Yeah, very good. A hydrogen ion is just one proton, no electrons, because it's lost its valence shell electrons, right? The one valence shell electron it had. So a proton is a H plus. Amphi should kind of remind you of ambi, like ambidextrous, can do both. An amphiprotic substance can release hydrogen, aka act as an acid, or it can neutralize hydrogen, aka act as a base. So amphiprotic substances can act as acids or bases. And they must contain H plus. That is one other huge criteria. We'll come back to this. Okay, in the next theory, all of this will be explained. An example of an amphiprotic substance is this ion here, the bicarbonate or hydrogen carbonate ion. We'll come back to that as well. Just put EG for now. Good. Do we have any questions so far? As you can see, there are 3 main pros, 3 main cons, but I think it's for a band 6 answer, remember all 4 pros and cons. This would be very high yield. I think this table is probably the most high yield part of this dot point, because the next theory is what you'll be using for the rest of HSC chemistry. Now, has anyone learnt Bronsted-Lowry theory? Can you maybe raise your hand or nod? Has anyone heard of Bronsted-Lowry theory before? Yeah, well, good. Well, this is good learning. This is the theory you'll be using from this point onwards through the rest of HSC chemistry, right? Now, Mithilesh, what was the main issue of Arrhenius theory? The one error you must say.
He could not explain the metal oxides and carbonates.
Well, I would not say it's a main error. That's one of the supplementary errors of that theory. What was the main error I told you about? What did the ammonia dilemma highlight?
It doesn't have to occur in an aqueous solution.
Exactly. It could not explain acid-base reactions outside of aqueous state, aka it did not account for different solvents. Okay. Now, Bronsted-Lowry theory explains the role of the solvent. That is the main strength. In fact, remember this, all the cons of Arrhenius theory are all the pros of Bronsted-Lowry theory. That's why it's very easy, right? All the cons of Arrhenius theory are now the pros of Bronsted-Lowry theory. So we'll talk about this. Have a look at the definition. So this was proposed in the early 1900s, and two scientists, Bronsted and Lowry, proposed that acids are proton donors, bases are proton acceptors. Very simple definition. Do you see how there's no mention of a solvent, there's no mention of aqueous, proton acceptor, proton donor. That's all you need to say in your exams. In fact, they'll never ask you to define it because it's too easy, but that's the principle there. Now, Rias mentioned that a proton is just a hydrogen ion, right? Nonetheless, you're not going to say hydrogen ion donor, hydrogen ion acceptor. You'll call it a proton because that is what the theory is stressing. And just understand a proton is just a hydrogen ion. So in a neutralization reaction where you have an acid and a base, does everyone agree you'll have an acid that's donating a proton? You have the base that's accepting a proton. Thereby, you must have a proton transfer from the acid to the base. Everyone agree? Now let me show you what this all looks like on paper, because so far it wouldn't make much sense until you write it on paper. So let's pick a very easy acid, HCl. Now, according to Arrhenius theory, HCl simply ionizes to H plus and Cl minus. Everyone agree? Everything's aqueous. I will include the states just to stress how important that was. But according to Bronsted-Lowry theory, we write the reaction slightly differently now. We will write HCl, but we are going to include the solvent in the reaction. Gerald, what is a solvent?
Water.
Yeah, so water is going to be included in the reaction like this. Okay, and now we're going to apply the principles of Bronsted-Lowry theory. Risa, what did we say an acid was again?
Acid releases hydrogen ions in.
Yes, but remember now you're going to erase all of those past theories using Bronsted-Lowry theory only from this point onwards.
Acids are proton donors.
Good. Now, what did we say a proton was? It was just a hydrogen. We all agree it's a hydrogen ion. So to donate a proton, the HCl must give its hydrogen to the water. Okay, so what happens then? The water is going to get an additional hydrogen. It's going to form H3O. And since it was a hydrogen ion that it obtained, do you all agree? Oh, what happened there? Go up. Yeah. Its charge is going to be +1. Everyone agree? What do we call the name of this ion? It's a very important ion.
Hydronium.
Very good. Now, extension question. What kind of unique bond exists in the hydronium ion?
Coordinate covalent.
Very good, right? And it's that case where the hydrogen ion had no valence electrons. It can't share electrons because it has no electrons. So what it does, it's a bit cheeky, it takes both the electrons of the oxygen and it forms a bond like this. So both of these electrons are coming from the oxygen, but it's still a covalent bond. So it's called a coordinate covalent bond. Very good. And what remains of the HCl, everyone? Just a Cl minus. Now I have a question for you. What is water behaving as in this reaction? We agree that HCl is an acid because it's donating a proton. What is water doing? And thus, what can we say water is?
It's a basic substance because it's accepting a proton.
This is very interesting because now, rather than saying bases are just intrinsic to substances, being acidic or basic is a behavior. Do you all see that? Water is behaving as a base in this scenario. It doesn't always do that. In this scenario, it is behaving as a base because it's accepting a proton. Very good. Now, I'm going to introduce two additional terms that we use in Bronsted-Lowry theory. They're called conjugates. Now, you'll see this acid here, right? Whatever happens to the acid on the other side of the equation is its conjugate. So this is the conjugate of the acid. And to be specific, we call the conjugate substance of an acid the conjugate base. So Cl minus is the conjugate base. Okay? And similarly, H2O was a base. So if we follow H2O to the other side of the equation, what do you think we'd call that? Again, we'd use conjugate, but instead of calling it a conjugate base, what would we call it?
Conjugate acid.
Yes, there you go. Conjugate acid. Okay? And the reason we do that, everyone, is because I want you to imagine if there was a reversible error, imagine the reaction went backwards. What would the Cl be doing? So now look right to left. Look from the products to the reactants. If Cl went backwards, what would it be doing? Would it be accepting a proton or would it be donating a proton?
Accepting.
Good. So do you all agree it's acting as a base, right? And what would the hydronium be doing? Donating or accepting a proton?
Donating.
There you go. So it's acting as an acid. Does everyone agree? So that is why we call the conjugate of an acid the conjugate base. We call the conjugate of a base the conjugate acid. So acid becomes conjugate base, base becomes conjugate acid. Everyone with me? Now, here's your challenge question. You all know HCl is a strong acid. And why is it a strong acid, Riasat?
It ionizes to completion.
Very good. How do you know that? It's because this arrow is going in only one direction. You agree? Good. So strength is all about degree of ionization. If it ionizes to 100%, it's strong. If it does not ionize at all, it's a very weak. If it partially ionizes, it's weak. Make sense? Now, can anyone tell me what would be the strength of the chloride ion as a base? Because we've identified the chloride ion is a base. What would its strength be? Would it be strong, weak, or very weak? AKA, is its degree of ionization 100%, less than 100, or is it 0?
0.
0. So if its percentage of ionization is 0, what is its strength? Very weak, weak, or strong?
Very weak.
Good. So you just made a new principle, and this is a universal rule. The conjugate of any strong acid or base is a very weak base or acid. Okay? And it makes sense because the arrow will never go backwards. So it'll always be the case that the conjugate of any strong acid or base will be a very weak base or acid, aka 0% ionization. And it's strong because it's 100% ionization. Good. So a few new terms here. I'm going to give you all another reaction. You'll realize you're going to be doing this for the rest of HSC Chemistry, Bronsted-Lowry equation. So this will become like basic English to you very shortly. So I wouldn't worry too much about all the details, just understand what's going on. Any questions so far? Good job. All right, let's go to the next equation. So I'm not going to write anything. I'm just going to give you the base of the acid. CH3COH. I want you to write the equation for this, this acid in terms of Bronsted-Lowry theory. Remember, from now on, you are not doing a single Arrhenius theory equation. All equations must be in Bronsted-Lowry theory. So, of course, what will the acetic acid be reacting with, Gerald?
Water.
Good. And we would form. And recite, would it be single directional arrows or double directional arrows?
Would this be double directional because it's
because it's
a weak acid?
Very good, right? Because it's weak, it'll be double directional arrows. Good job. So what's going to happen now? So Mithilesh, which hydrogen of this acetic acid is actually the proton that can donate? Only the last one, right? I think you'll remember, whenever we talk about carboxylic acids, it is only the COOH group, it is only the H at the end that can act as an acid. So I want you to remember that all these hydrogens will not, because this is the methyl group. Remember methane, where I taught you about methane having 4 hydrogens? When methane's attached to another main chain, it will have 3 hydrogens. But nonetheless, those 3 hydrogens will never, ever be ionized as an acid. So that is why those 3 hydrogens will never be removed. Good. So we've got CH3COOH, we've got H2O, and what do we form now? So I'll pass it on to Mithilesh. What are my products?
Hydronium and acetate.
Good. Yeah. Hydronium, because the water will gain a proton, aka it's acting as a base, so we can identify that straight away. And acetic acid is acting as an acid because it's donating a proton or a hydrogen. And so we're left with CH3COO minus. So Gerald, what's my conjugate acid and who's my conjugate base?
The conjugate acid is the hydronium, and the conjugate base is your acetate.
Good. And my conjugate base is my acetate. And now, Risa, I guess this is the final question. What can you tell me about the strength of the conjugate acid and the strength of the conjugate base? So I will start with a most important one. Tell me about the strength of the, apologies, I should have written conjugate base here. This is your conjugate base. So what would the strength of the conjugate base be, Riyasat?
The strength of the conjugate base would be weak.
Good. Why is it weak?
Because since there is a double directional arrow, that means it has less than 100% ionization. But
very good. And what's the strength of the acetic acid?
Strength, it's also weak.
Very good. So Resat's now uncovered the second principle. The conjugate of a weak acid or base is a weak base or acid. That's it. The conjugate of a strong is very weak. The conjugate of a weak is weak. That's the key point you need to remember. Does that make sense? And if you get confused or if you forget, you can always just write out an equation and logically derive it as Resat has done here. Does that make sense to everyone? Good. Good. Remember, it's not very weak because there is a reaction occurring. So degree of ionization is greater than 0%. But it is weak because it's less than 100. Very good. Good job. So you can just see, this is just a textbook image highlighting exactly what we said. So conjugate acid-base pairs. What you'll notice, everyone, this is a small pointer. They always differ by 1 hydrogen. Do you all notice that? So conjugate acid-base pairs always differ by 1 hydrogen. Okay? There's just an important point to notice. All right. Let's move on. Now, strengths. What did I tell you all? I'm not going to go through all of this. How do you remember all the strengths of Bronsted-Lowry theory?
The weaknesses of Arrhenius' theory.
Good. So let's start going through the weaknesses of Arrhenius theory. So what was the main weakness, Riyasat?
The main weakness was to explain the role of the solvent, or explain
of the solvent. Good. Now I want you all to look back at this equation, the same equation that stuffed Arrhenius theory up, and explain it to me. How does Bronsted-Lowry theory explain this is a neutralization reaction? I will get Gerald to explain.
So in this reaction, the ammonia acts as a proton donator.
Is it acting as a proton donator? What's happening to the ammonia?
Actually, no, it's proton acceptor.
Yeah.
Right? Yeah.
Do you see that the H is going from the HCl and it's going to the ammonia to form NH4? And the remaining Cl is just binding to whatever's left, right? So the key thing here is the HCl is donating a proton, aka it's acting as an acid. So let's identify that. It's acting as an acid. And the NH3 is acting as a base because it's a proton acceptor. So Mithilesh, who's the conjugate acid and who's the conjugate base? I know it's a solid state, so you can't really separate the two, but out of these two.
Okay, so the conjugate acid is ammonia.
Good.
I mean, yeah, NH4 and
Yeah.
ammonium, and the conjugate base is Cl minus.
Good, good. But as you all know, since this is solid, there's no ions per se, so they would never ask you for conjugates for this reaction. But very good. If there were, that would be the case. So that makes sense. So now you understand the first pro. It always will account for the role of the solvent. In fact, look at these reactions. The solvent is in the reaction itself. Do you all see that? So always will explain the role of the solvent. The next pro or con. Metal oxides and carbonates. It could explain metal oxides and carbonates. How so? It always explains metal oxides and carbonates will release hydroxide ions, and those will act as proton acceptors. So if we were to do a reaction, if it was sodium oxide, when sodium oxide combines with water, it'll form sodium hydroxide. And you can balance this yourself. But then the sodium hydroxide will then release sodium plus hydroxide ions. And the hydroxide ions can combine with any acid and thus engage in what kind of reaction, everyone? Bronsted-Lowry proton accepting reaction, right? So it can accept a proton and form water, and the remaining will be Cl minus. That's how Bronsted-Lowry theory can explain the acidic or basic nature of oxides and carbonates. This is very low yield. I've never ever had to write a reaction. As you can see, just long, tedious, and there's nothing difficult about these reactions. So you will never be asked to write those reactions there. What are some other pros of Bronsted-Lowry theory? Let's talk about amphiprotic substances. Now, I gave you your example of an amphiprotic substance as the bicarbonate ion here. Now, what is the definition of amphiprotic again? We'll ask Risat, what's the definition of amphiprotic?
It acts as both a base and an acid.
Very good. It acts as both a base or an acid. Good. So what you see here is it's acting as both a proton donor in an acidic solution, or it's acting as a proton acceptor in a basic solution. Now, can you see that they've written two reactions with bicarbonate reacting with water? That's not entirely correct, because bicarbonate in water would typically follow the more basic route. So this is a reaction that will predominate. So to avoid confusion and not lose any marks, the correct set of reactions you should show would be these. So if you were asked to write a reaction to explain any amphiprotic substance, you write one reaction for that substance in the presence of an acid, and one reaction for the substance in the presence of a base. Now take me through it. So I'll ask Mithilesh, for the first reaction, what are my products?
Okay,
So this is a thing, right? The hydronium ion is a strong acid. You have to remember that. It's always a strong acid. And the OH minus ion is a strong base. And I know you might think, wait a minute. The arrows are not single directional, however. That's fine. This is like a special case because hydronium is the ion that all acids are releasing. So always remember, this is a strong acid ion. This is a strong base ion. Okay? So it will always act as an acid or base. You'll never have a hydronium ion that's going to accept a proton. Never will form H4O2 plus or something. Okay? So Mithilesh, this is going to donate a proton. So what am I going to get as my products?
H2CO3 and H2O.
Good. And quickly label, what are my acid base? So this is my acid, that's my base. So what's my conjugate acid and base?
So conjugate acid is H2O. Never
Is
mind.
it?
No, it's H2CO3, and the conjugate base is H2O. Yeah.
Good. Remember, always just follow through. What happened to the acid on the other side? That's the conjugate base. Whatever happened to the base on the other side, that's a conjugate acid. In this case, this is your conjugate base. Good. Let's follow this second one. So I'll get Risat. what will I get as my products for the second reaction? So now OH is always going to accept a proton because it's a strong base. So what are we going to form?
CO3 2 minus and H2O.
Can you hear me, Risa?
Oh, yeah. Can you hear me? Can you hear me?
I think his camera is frozen.
I think, yeah.
Sorry, could you? Yeah, I can hear you.
Yeah, okay. Yeah, I said CO3 2 minus and
Okay, so we get
yeah, CO3 2 minus and
sorry,
H2.
I think it's my internet. I'll write it for you. You're right. You will get, this is your strong base, so you're going to get CO3 2 minus, as you said. Good. All right, so reset again. What's my acid base and conjugate pairs?
So the conjugate acid is H2O and conjugate base is CO3 2 minus.
Good. So since this is my base, my conjugate acid, that is your acid. So my conjugate base, as you said, is CO3 2 minus. Good. Good job. Any questions, everyone? So all I'm stressing here is make sure for amphiprotic substances, you show it reacting in acid and base solution, not in water twice. Okay, good. So bicarbonate is one key example. I'll give you all a tip. There are a couple of others. Tell me what the commonality is. So another amphiprotic substance would be HPO4 2 minus, H2PO4 3 minus. Another one could be we said HCO3. These are the three main ones you should know. Water can itself be amphiprotic, but it's an exception. What do all three of these ions have in common? Gerald?
They all have a charge of -1.
Yeah, sorry, I think my screen is a little bit laggy. You might not see, I've already written the names of the ions. But yeah, HPO4, H2PO4, HCO3 all have a negative charge, and they all have a hydrogen. So whenever you see a compound containing hydrogen, it can donate the proton, and since it has a negative charge, it can accept a proton. Does that make sense?
Prithvi, isn't it H2PO4 minus? Not 3.
H2PO4, yes, apologies. No, that's my bad. It's not 3 minus, completely right. It's H2PO4 minus. Good, thank you. Yeah, so as long as they have a negative charge and a hydrogen, they can potentially be amphiprotic. Very good. Now, let's start moving on. So we'll start talking about the cons of Bronsted-Lowry theory. There are two main cons here. Have a read of this. Okay. The first con is it could not explain amphoteric substances. Now, this sounds a lot like amphiprotic, so students will mix this up a lot. The way you understand this is amphoteric is an umbrella term for any compound that can act as both an acid or base. That is what amphoteric means.
Sorry, I can't. The screen's completely stuck. I can't see.
Oh, is it?
Yeah.
Okay, sorry. Let me unshare and reshare. How about that? Yeah, I can see that as well. I don't know why that's the case. Let me just share again. How about, is it frozen again? 1 second. Yeah, good. So as I was saying, amphoteric is the umbrella term for anything that can act as an acid or base. Amphiprotic is a branch of amphoteric. So amphiprotic is a branch of amphoteric where the substance has a proton or a hydrogen and thus can act as a Bronsted-Lowry acid or a Bronsted-Lowry base, aka accept or donate protons. Does that make sense to everyone? I'll show you what I mean by this. Have a look at aluminium oxide. Aluminium oxide is an amphoteric substance. Now, Gerald, does this substance contain a hydrogen?
No.
No, it doesn't, right? So it can't be called amphiprotic. It does not have a proton to donate or accept. Does everyone agree? So amphiprotic is out of the table so far. But what is it doing to sodium hydroxide, and what is it doing to HCl? It's forming a salt, and it's forming
Water.
water. It's neutralizing acids, and it's neutralizing bases, aka it's acting as an acid in a basic solution. It's acting as a base in an acidic solution. So what would we call this kind of substance, Smithlesh?
Amphoteric.
Yeah, that's it, right? So pretty much the main issue of Bronsted-Lowry theory is there are acids and bases that don't even have protons. Bronsted-Lowry theory can't explain that. And I guess that's the second error. Could not explain the behavior of non-protonated acids or bases, aka acids or bases that don't have H. Good. You do not need to know examples of this. I guess the only thing I might remember if I want to get a strong band 6 is just one example of an amphoteric substance. So aluminium oxide is a good one to have. But you do not need to know these reactions. This is out of the scope of the syllabus. It's just for you to understand what goes on. Okay? Good. So again, this is extension, and the reason that I will teach it to you is for Sydney boys, they can ask this in your trial paper. In the HSC, they'll never ask you this theory. So the most recent theory of acids and bases is called Lewis theory. And the way I remember Lewis theory is you swap proton with electron pair. We're now not looking at how protons are being transferred. We're zooming even closer to the subatomic level, and we're looking at electron pairs being accepted or donated. Okay? And it's the exact opposite of Bronsted-Lowry theory. So if Bronsted-Lowry theory said an acid is a proton donor, according to Lewis theory, it's an electron pair acceptor. And if we say that a base is a proton acceptor, according to Lewis theory, it's an electron pair donor. Let's talk about how this makes sense. So I've taught you how to memorize it, which is all you will need to know for the HSC and trials. But let's truly understand it here. Now, everyone, what's happening in this reaction? Do you all see there is a hydrogen ion, and it is combining with ammonia, which is NH3, which is a base, to form ammonium. Everyone see that? Now, let's look at it in terms of Lewis theory, right? Do you see this hydrogen is going to combine with the ammonia, but what is the hydrogen doing? Is it donating this electron pair, or is it accepting an electron pair from ammonia and forming a coordinate covalent bond? Does hydrogen have any electrons, Mithilesh?
No.
No.
No. So it can't be donating an electron pair. It's got no electrons at all. But what can it do? It can accept an electron pair and form a coordinate covalent bond, right? As you see right here. And so hydrogen is acting as an electron pair acceptor, aka we call this a Lewis acid. And the ammonia, what is the ammonia doing? It's got a free electron pair. Do you see it's donating the electron pair to the hydrogen? Right? So since this is an electron pair donor, it is therefore defined as a base, according to Lewis theory. Okay? And you'll realize this checks out for every single reaction you've studied so far. Have a look at this. I'm going to quickly zoom up. But every single reaction you've studied here, maybe I'll give you this one, for example, right? You can also explain it in terms of Lewis theory. Because how did this hydronium, actually not this reaction here, you can still explain this one, but we'll pick a simple one, such as this one, right? If I zoom in here, according to Lewis theory, we had water. And what's the structure of water, everyone? It's this structure here. Everyone agree? Now, what happened to the hydrogen of the HCl? It formed a coordinate covalent bond with the water. So who was the Lewis acid? Who was the electron pair acceptor?
The hydrogen.
Yeah, it was an electron pair acceptor, so we call that the acid. The Lewis theory is saying it's not really the HCl that's the electron pair acceptor, it's a hydrogen ion that's acting as the electron pair acceptor. And who's the electron pair donor?
The water.
Yeah, it's forming coordinate covalent bond here. It's the electron pair donor. That's it. So according to Lewis theory, the H plus ion is the Lewis acid and the water is the Lewis base. That's it. Okay. Now, all of this, again, is very likely not going to be tested. So I wouldn't worry about Lewis theory at all. I'd focus on Bronsted-Lowry theory and Arrhenius theory. Are we happy to move on? Okay. In the next hour, we're going to go really deep into pKa, Ka calculation questions. We're going to do some really challenging calculation questions. So what I might do before we do that is I'll give you a 5-minute break now. And then till 4:30, we're going to be doing quite some challenging calculation questions. So stand up, stretch, get a break. And if you can solve the questions that I put forth in this lesson, I think you'd be quite set for calculations in chemistry. All right. So take your break, get some water, and we'll resume at 3:36-ish. Okay? All right. See you guys there. Okay, when we're back, be great if you could turn your cameras on. We'll jump back into it. Okay, and Mithilesh, are you back?
Yeah, I'm back.
I think you're lagging again, Prithvi.
Sorry, I think my connection had been a bit bad then. Can you hear me fine? Good. All right, let's jump into it. So the next inquiry question is, I'll get Gerald. Do you mind reading out for us?
What is the role of water in solutions of acids and bases?
Gerald, what's your answer to that question? Because remember, with every inquiry question, you want to have a broad answer, and then you will elaborate upon it by doing the remaining dot points. So what is your one-line answer to this question?
Depending on the substance, it acts as like the opposite. So if it was an acid, it would act as a base, and if it was a base, it would act as an acid.
Okay. It acts as a proton acceptor or donor, enabling other substances to act as an acid or base. To act as a Bronsted-Lowry acid or base. Very good. So that's your one-line answer to this inquiry question. Very good. Good job. Now, this dot point practical investigation is all really fluffy. You'll be doing this at school via prac. You'll typically be using red cabbage. Has anyone created the red cabbage indicator at school already? Yeah? Okay. So, Risa, tell me, what's the name of the actual indicator in the red cabbage?
I actually don't know. We only just recently did it. I mean, like the last thing we did was that we didn't really talk about what is in it. That
Oh, okay. Yeah, they should have gone through that because that's why you're learning that, not just playing with cabbage. So
Right.
yeah, the indicator is called anthocyanin, and that's the indicator you're trying to extract. So you would have all boiled cabbage leaves until you extracted the anthocyanin indicator from the cabbage leaves. You would have then decanted or filtered the cabbage leaves so that you just got a solution of anthocyanin. And Jared, what color is anthocyanin?
I'm guessing red.
Yeah,
Or
it's a
purple.
purpley. Although it's called red cabbage, it has a reddish purple color, right? It's not pure red. So yeah, you have a purpley red solution, and then it's going to change color depending on what household substance or solution you test it with. So I would not memorize any of this. I would just remember the key principles, which is what we just went through. And Mithilesh, with any scientific method, now in the HSC, it's very unlikely they will ask you to write a method up because that's just memorization and that's not what the HSC tests. But if you were to do it for a depth study or an assessment, Mithilesh, what are the three things that you should always have in a method?
Okay, so clear steps, I guess, one, and then like specific like measurement tools.
Good. So verbs.
Yeah, instructive
Equipment.
equipment and I don't remember the third one.
Quantities.
Quantities, okay.
Right? Yeah. Those are the three things you must have. So don't worry about memorizing an entire method or any method for chemistry or even physics. If you generally know the idea of that method and then you ballpark figures of quantities you would use, what equipment you'd use, you will always get it correct. Okay, so verbs, equipment, and quantities is more than sufficient to get the full marks. I'm not going to go through this because you've already done this at school and you will learn much more from seeing it being done and doing it yourself rather than reading lines on paper. So here's the color of red cabbage. As you can see, it varies, goes to a yellow and to a red in acidic solutions. You don't need to memorize the color changes at all. But if you were to explain why it's changing color, Gerald, how would you explain that? One line explanation. So why is anthocyanin? So if it was an exam question, it would be, explain the color changes observed of anthocyanin in various acidic and basic solutions.
The concentration of anthocyanin varies depending on solutions added to it. So if it was a more basic solution, then it would be neutralized. Therefore, there would be less anthocyanin in solution, thus decreasing concentration and changing its color.
Okay, I would still not give full marks there because you're missing a very important point. Mithlesh.
Maybe it forms an equilibrium and then.
Good.
Something
And
like
what do all equilibriums obey?
Le Chatelier's principle.
Good, right? So these color changes are due to shifts in the relative concentrations of the ionized and unionized forms of anthocyanin. And those will have two distinct colors. In this case, it's a red and yellow. And that's why in the middle, it has a purple color or appearance. Does that make sense? That's how you'd explain that. So anthocyanin is likely a weak acid that forms a chemical equilibrium, and its ionized and unionized form will have two distinct colors. And according to Le Chatelier's principles, when added to acids and base solutions, the intensity of the respective ions would change, resulting in a color change in the indicator. Something along those lines. Right? You all learned this. Do you remember when I explained to you how indicators work? So I was testing that dot point. That's much more high yield than this prac. All right, now here is where we get into the actual calculation part of Mod 6. A lot of students find this challenging, but I'm going to make this very easy for you through practice. Now, have a read of the dot point. So calculate pH, pOH, hydrogen ion concentration, and hydroxide ion concentration for a range of solutions. So the key equations you need to know are all written here, which is pH equals negative log 10 of the hydrogen ion concentration. pOH is the exact same, but for hydroxide ions. And then you've got this equation here, which is pH plus pOH is equal to 14. Now, I want to just preface, all of these equations are applicable only at 25 degrees Celsius, okay? That's where you can use these equations. Now, most of the time in calculations, I will tell you that. The reason I'm mentioning this is distilled water restart, what will its pH be?
7.
At 25 degrees. If you're away from 25 degrees, the pH of distilled water itself starts to change. So it's an important principle, and we'll explain why. I want you all to understand this. Now, the way we get all of these equations, everyone, is we look at water itself. Now, when you look at water in a beaker, water does not just exist in molecular form. So 99% of water will exist as water molecules. But a very tiny fraction of water, what it will do is it will react with itself like this, 2H2O, and it will form an equilibrium where it forms hydronium ions and it forms hydroxide ions. And these will spontaneously react with one another and reform water. So a very small percentage of water is doing this equilibrium reaction in any beaker. So every time you get a cup of water, a very tiny percentage of your water molecules are engaging in this kind of reaction. Now, what would the equilibrium constant expression be for this, Gerald?
Concentration of hydronium times concentration of hydroxide.
Okay, good. Now, at 25 degrees, this Kw equals to 1 times 10 to the power negative 14. Okay? Now, here's your challenge. Using this, I want you to prove to me that only at 25 degrees is pH plus pOH equal to 14. That's your first challenge. Derive that equation for me. So you have about 2 minutes. Do it as fast as you can. And you realize once you start deriving these formulas, you will truly understand when to use them, how to use them, much better than a student that just memorizes them. Good. When you get an answer, raise your hand so I know you've got an answer as well. Okay. Very good. All right, let's jump into it. So, okay, so Risa, can you explain to me what you did?
So the concentration of H3O plus I need that would pretty much be the same as the concentration of, I guess, H plus from that from the equations there. So I changed it to 10 to the minus pH, 10 to the power of minus pH.
Oh, so you use this, you sub this in, is that right?
Yeah.
Oh, yeah, look, that works, but I wanted us to not use any of these equations and then come to this conclusion.
Oh, okay.
So like you'd only have to use this equation and this equation. So how about this? What if I logged each side, right? If I did log 10 of hydronium times hydroxide equals to log 10 of 10 to the power negative 14. What do I get? What can I simplify that to?
Minus 14, yeah.
Yeah. So what can I convert this into? Because I want this to look like POH and POH, right? So can I not do negative log 10 of hydrogen times hydroxide equals to 14, right? And can we not simplify that into equals to negative log 10 of hydronium plus negative log 10 of hydroxide equals to 14. And that would be pH plus POH equals to 14. Let's go up there. Does that make sense? So that's how you would do that. Now, another challenge for all of you. Can you prove to me that the pH of water is exactly 7 at 25 degrees using this equation here? And the only other equation you're allowed to use is this. So again, 2 minutes. And after that, we will move on to some other challenge questions. And this is they asked this in one of the trial papers. So to calculate the pH of water at a different temperature. So once you can do it at 25 degrees, you follow the same principles and you get the pH at different temperatures. Good. Let's start. Joel, any ideas on what we do?
Not really, but the way I thought about it, I was just like, because by equation we know that concentration of hydronium and hydroxide is the same.
Good.
That would mean that pH plus POH is equal to 14. So you just divide it by 2 and you would get answer.
Oh, yeah, look, that you can do it that way. Yes. Yeah. I'll show you the way I was planning on you all solving this. So you could get hydronium ion concentration squared is equal to 1 times 10 to the power negative 14. And so we can then log each side, right? Or we could even square root it. And we can say, therefore, hydronium ion concentration itself is equal to 1 times 10 to the power of negative 7. And then if we log 10 of hydronium ion concentration, we should get that equals to log 10 of 10 to the power of negative 7, which is just negative 7, right? And then if you multiply each side by negative, you get log 10 of hydronium is equal to 7. And what is negative log 10 of hydronium? That is what we call pH. So pH of water only at 25 degrees is equal to 7. And you can imagine if this K constant changed, you get a completely different value for the pH of water. Does that make sense? Good. Good. So now that you understand all these equations, I'm going to introduce a few new equations for us. So all of this is what we just did. So let's move on and we'll go to these equations. Now, these equations are very high yield. I guess the first most important equation is about pKa and Ka. Now, what is Ka to all of us?
That's the constant for acids.
Yeah, it's the equilibrium constant for an acid. So when an acid ionizes and it forms hydronium ions and the A- ion, the K value is Ka. Does that make sense? So if we have a strong acid, I want us to think about this. A strong acid. What will its Ka value be if it's strong?
It would be very high.
Yeah, strong acid will have a high Ka. Now, what would that do to pKa? Because remember, pKa is negative log 10 of Ka. Does everyone agree? It's going to be like pH. It'll be an inverse relationship. pKa would be very low. So that's very important to understand. Mithilesh, what about a strong base? What would its Kb be?
High.
Yeah, so what would its pKb be?
Low.
Yeah, so that's a very important trend you need to understand. Now, what did I tell you all about concentration and strength? Are they related or independent?
Independent.
Good. So all the pH formulas you learned are all about concentration. All the Ka-pK formulas you are learning now are all about strength. Does that make sense? They're separate, okay? So you can't directly go from one to another, describe strength in terms of pH or concentration in terms of Ka. It doesn't work like that, okay? Very good. Now, the final equation I want to explain to you is this one here, which is a very high yield equation because students forget it. And so in trial papers, they love this equation. Ka times Kb equals to Kw. Now we're going to derive that equation together. Let's pick a weak acid. Let's pick acetic acid. Right? So let's write the equation for acetic acid ionizing in water. And that would be Ka. Now, what would the conjugate base of this reaction be? Riasa? We get H3O plus. What else do we form?
Acetate.
Yeah, so the conjugate base is acetate. So
Yep.
now we need to write another reaction with a conjugate base, which is acetate, also combining with water. This is the key thing. We need water here on both sides for the reactants. You need that. Very important. So when this reaction happens, you'll form hydroxide ions, and you'll also form CH3COOH. And this is a reaction for Kb. So as you can see, when an acid combines with water, the reaction is Ka. When the conjugate base combines with water as well, that reaction is defined as Kb. Does that make sense? Now, I want you all to prove to me that Ka times Kb will give me this value here, which is a self-ionization of water. It's a slightly easier one to do. So again, when you do this, raise your hand and we'll go through it. It's not a hard one. This definitely can be asked in the HSC. The others were a bit of two-unit maths, but this one is very simple. Okay, have we got an answer? Good. Risa, I guess start us off. Can you explain how K times Kb gives me this answer?
Yeah, so I wrote what Ka is, which is which is the okay, I'll just wait for it's the concentration of acetate times the concentration of hydronium over the concentration of acetic acid.
Good.
Yep.
That is Ka.
That's
Concentration of acetic acid. Good. I like that you didn't include water. If you did include water, just know that would be 1. You could include the expression for water, but you'd sub in the value of 1 for that.
Yep.
Good. And what's Kb?
Kb is the concentration of acetic acid times the concentration of hydroxide over the concentration of acetate.
Good. So when you multiply K times Kb, what do you get?
Since the acetate and the acetic acid both cancel out when you multiply.
Good. So have a look at this. The denominators and will cancel out with the numerator, as we can see that there. And the same way, the acetic acid, which is the numerator for Kb, is the denominator for Ka. So you end up with Ka times Kb gives you hydronium times
Hydroxide. Hydronium oxide,
good.
which from before we found is equal to Kw. Yeah.
Good. And at 25 degrees, that's 1 times 10 to the power of negative 14. Very good. Good job. The reason I made you derive this equation in particular is a lot of students are confused about this one, right? So now you know how to derive it. And remember, the key most important thing, everyone, is the big mistake students make is they'll write the correct expression for Ka, but they'll write the equation for Kb as the exact opposite of Ka. So they'll show the acetate ion combining with hydronium. It is not with hydronium. What is the Kb reaction? It's the conjugate base combining with water. Can't stress it enough. Water must be on the reactant side for both equations. Does that make sense? All right. I think you're all ready now to do the hard questions. Now, what I'm going to do is I'm going to throw you straight into one of the hardest questions. It looks deceptively easy. Look at that. 2 lines. So, I'm going to give you all about 4 minutes to do this question, all on your own. This was a very similar question to this was question 19 of the 2019 exam choice trial. So it's a really good calculation question. Good luck. Using all the pH, pKa, K equations you learnt today, using Rice tables if needed, whatever you need, aim to solve this question. And remember, don't just think about what you learnt today, think everything chemistry that you've learnt so far, and you should be able to get this question. So when you get your answer, raise your hand, okay? Okay, I think I've given you all quite a bit of time now. So, is anyone completely stuck? Or are we still working towards a solution? Working towards a solution? Kind of? All right. It's a good question. I told you all, it would be challenging. Would you like me to start prompting, or do you think you'd like a bit more time to do it yourself? What's the consensus we're getting? Mithilesh?
2 minutes more, maybe.
Okay. Gerald? Happy with that?
Yeah, happy
Okay.
with that.
Restart. All right. I'm going to give you all exactly 2 more minutes, and then we'll start going through it. Okay. My general tip is treat this like the last exam question. Follow the steps we've always done in class. Okay. You'll get to your answer. Okay, let's start going through this. So, has anyone gotten close to an answer or got an answer? Okay, that's all right. As I told you all, this is a very challenging question. I think more than 70% of students sitting the HC exam would not be able to solve this one. So don't fret at all. Let's do this together. So I'm going to guide you. I'm not going to spoon feed you. So it still requires you to think critically here. Now, what's the first step I do? If I am your stuck friend doing this question, what would you advise me to do first?
Equations.
Yeah, exactly, right? So what's the first equation we have? It's carbonic acid solution. So, Mithilesh, what would the equation look like?
Carbonic acid plus water.
Yep, gives me
Hydronium and hydrogen carbonate.
good, right? So he's used Bronsted-Lowry equation, which is good. All right, and is it balanced? Typically, all Bronsted-Lowry equation would be balanced because it's always just one proton just transferring across. So you don't need to worry too much about balancing. Good. So what data do I have about this, Gerald?
Well, you know that it reacts in a 1-to-1 ratio. So there's an equal concentration of hydronium to.
But what data do I have? Remember, now you're making inferences
Right.
from the data. I want to know what raw data do I have?
So you have a 0.2 molar solution of sodium hydrogen carbonate.
Have you missed a few numbers when you went straight down to the second sentence?
Well, pK is 6.35.
Good. You want to write everything, because if you miss even one piece of data, it could stray you from the question. So pK is 6.35. Temperature is 25 degrees. Good. And now you can tell me, well, the pH of a 0.2 mole per liter sodium hydrogen carbonate solution. Now, Risa, do you see sodium hydrogen carbonate in this first equation?
No, not sodium hydrogen carbonate.
No. So what do you think we need to do, Risa? Do you think we need to work with the current equation or add a second equation?
We have to add a second equation.
Good, right? Now, when we think of sodium hydrogen carbonate, what does it do? Sodium hydrogen carbonate in water, since it's a group 1 metal salt, will ionize, it'll dissolve to form sodium ions and what ion?
Hydrogen carbonate.
Good, right? Now, what's the hydrogen carbonate ion going to do in water? Gerald?
It's going to accept a proton.
Yeah, very good. It's going to act at it. Very good that you picked that up. I kind of cued you all into it earlier in this lesson, which is that this is an amphiprotic substance, but in water, it tends to act slightly more as a base. So if you were to pick one equation, it'd be in water, and it would be accepting a proton. So we'd form hydroxide ions, and we would form carbonic acid. Very good. All right. Okay, let's say I'm still stuck. I have no clue what to do now. Mithlesh, what should I do next? So I've done equations, I've done data. Do you think this is complicated enough to require a diagram?
No.
Yeah, the reason I say it's not is because, sorry, I'll add the concentration as well. So concentration of HCO3 minus with 0.2 moles per liter. Yeah, there's no volumes here. Does everyone agree? Whenever you have multiple volumes combining or dilutions, that's when you add a diagram. Now there's not really much utility. I'm still stuck, Risa. What do I do next?
I'm not sure. I got lost as well.
Gerald, what do I do now? Still stuck.
What I did was I found the equation for KAKB. So
Before you do that, before you start
well,
any calculations, remember, what are the steps I told you all? Equation, data, diagrams, anything else? Mithlesh?
No, I don't know.
Can't be forgetting this, guys. This is why I stress there are 5 things you typically always do with every single calculation question. Equation, data, diagrams, and then frame the question. What I mean by that is, what is this asking me? pH equals question mark. That is what it's asking me. Does everyone agree? And what equation is it asking pH of? The first or the second equation? Equation 1 or equation 2?
Equation 1.
Are you sure? It's asking for the calculate the pH of the sodium hydrogen carbonate solution. Is that equation 1 or 2?
Yeah, number 2. Yeah.
Good. So pH 2 equals question mark. Now, how do I find pH generally? Let's try working backwards to a plan of attack for this question. How do you find pH? Everyone?
Minus log 10 of the concentration of hydrogen.
Good. But Joe, do I even have any hydrogen ions in equation 2?
No.
No. So that plan of attack has already been cancelled. So we're going to cross that out. What else can I do? How else can I find pH?
14 minus POH.
Yeah, very good. And that means I need to thus find POH. Can I find POH? Well, it's got a hydroxide ion here. Does everyone agree? So if I could first find the hydroxide ion concentration, then I definitely can find POH. Does everyone agree? Now, how could I find concentrations The only other key data point I have is temperature. And why do you think they've given us 25 degrees? Just so we
because it
can
only
use
works at-
all the equations. Yeah. So all those equations are applicable only at 25 degrees. So I would say that's not too applicable to anything. So this must be our ticket to our answer, pKa. Now I have a question for all of you. When you have pKa, what can you find?
The concentrations of the conjugate thingos.
Yeah.
I mean, you can find Ka and then from
Yes, that's what I want to hear. I want you all to write this in red. It's so important. Whenever you have pKa, they are begging you to find Ka. Okay? And whenever you have Ka, what can you find, everyone?
Kb.
Yeah, you could find Kb, right? You could find Kb. And that takes you from the first equation down to the second equation. Does everyone agree? Right? Because one very important thing you may have noticed is this is the equation for Ka, and this is the equation for Kb. And the way you would have realized that is, wait a minute, these equations look so similar, and they both have water as a reactant, right? So that is why it's Ka and Kb equation. Good. All right, so if you've got Kb, Gerald, what can you find then? Whenever you have K, think about module 5. What can you find?
You can find concentration.
Yes, and Gerald, isn't one of the key concentrations we want to find hydroxide ion concentration?
Yeah.
And won't that take us straight to our answer? So do you all see how important framing the question is? When you frame the question, you pretty much already have a plan of attack before you start anything. So now we know we're going to use Ka times Kb equals Kw to find Kb. We're going to use a Rice table potentially to find concentrations. We're going to then find pOH, and then we're going to 14 minus that for pH. So even before I started calculating anything, I've got my answer. Does that make sense? That's why I'm stressing the most important thing you can do in a tough calculation question is frame the question. What is it asking me? How can I work backwards to find the answer? Good. I'm going to rub all this out, and we're going to start doing it. Good. So let's start doing it together. So what was the first step we said? We're going to use Ka times Kb equals Kw. Or what else could we use, everyone? What was another formula that used pKa directly?
pKa times pKb equals to 4. Sorry.
Plus.
Plus, yeah.
Yeah,
Plus,
pK plus pK. Remember, it's very similar to pH. So you remember pH plus pOH gives you 14. So pKa plus pKb equals 14. But we're going to do it this way that we decided. So let's find Ka now. So Ka is equal to 10 to the power of negative pKa, which is equal to 10 to the power of negative 6.35. Everyone with me? So what's Kb going to be? Kb times Ka equals Kw. So Kb is Kw divided by Ka, which is 1 times 10 to the power of negative 14 divided by 10 to the power of negative 6.35. So what do we get now as our answer?
one times 10 to the power negative 7.65.
Okay, sure. Let's store that as A. Okay, so we've got Kb. Now, everyone, what concentration is this? Because what did we say? From Kb, we're going to use a Rice table. So I need to know whether this is initial, change, or equilibrium. What concentration is that HCO3 minus from? Is it initial, equilibrium? What is it?
Wait, I'm not too sure about the value that we got for the division.
Oh, is
Yeah,
it?
I got a different value.
I got
as well.
2.239 times 10 to the power of negative 8.
Yeah, that's what I got.
Yeah, if you just check like if you put that in there, it gives the same thing. It's basically the same thing. I just used the pK.
Okay, yeah, sure. Okay, right. Either way, okay, so either way, we've got our answer for KB. Good. So we've got KB. Now, again, what was the answer to my question? This concentration of bicarbonate, is it initial, equilibrium, or final? Look at the question and read it.
Initial.
Good, right? Because whenever they tell you that there is a 0.2 mole per liter of a solution, that's the concentration they made it to. So at time equals 0. After that, the forward reaction will pursue. Some of that concentration will decrease and product will form. So this is an initial concentration. So what we're going to do now, everyone, is a rice table, right? So what are the substances? We've got bicarb. We don't care about water. That's a reactant. And then your product side is your hydroxide and your carbonic acid. Now, the initial concentration of bicarbonate was 0.2. Let's say it decreases by x. And so at equilibrium, it's 0.2 minus x. What about for hydroxide and carbonic acid? They start at 0. So, Gerald, what would their equilibrium concentrations be?
It would be plus x for both of them.
That's it. So, Risa, what would the expression for Kb be in terms of x?
It would be yeah, originals H2. Okay, so that in terms of x, it would be x squared over 0.2 minus x.
Good. So x squared divided by 0.2 minus x is equal to a. Now, I think you all can see that this is going to make a quadratic equation. And you don't want to do quadratics in chemistry because you don't need to ever use quadratics in chemistry. So we can apply the small change assumption and say only for the denominator, 0.2 minus x is close enough to 0.2. Okay, so simplifying that for us, we'll say that equals to, therefore, x squared on 0.2 is equal to a. So everyone, what is x equal to?
Uh, 6.691 times 10 to the power of negative 5.
Good. Let's store that as C. Now, what is x, Gerald? What did we want to find? So we've currently gone down this pathway. So we've found the rice table. And what were we going to do after the rice table?
We were going to find concentration of hydroxide.
Good. So what is x? Is it the concentration of hydroxide?
Yeah.
Good. So we can say concentration of hydroxide equals x equals to C. So what can I do now, Risa?
You can find POH.
Good. So POH is equal to negative log 10 of OH minus, which is negative log 10 of C. What do we get?
Um, 4.17.
4.17?
Yeah.
Yeah.
Okay, 4.17. And we can store that as D. So pH is equal to 14 minus D, and this is why we're using the 25 degrees. We can only apply this rule because the reactions are occurring at 25 degrees. So what's 14 minus 4.17?
9.8.
9.8.
9.83.
9.83. Did everyone get that value? 9.83. Now, how many sig figs should our answer be to? Mithilesh?
1.
Good. So you'd round this off to 10. 1 sig fig. Good. Now I want you to pause and think about this conceptually. Does it make sense for a sodium hydrogen carbonate solution to have a pH of 10? Yeah, kind of it does, because we said it's amphiprotic, but I told you in water it's slightly basic. So that checks out with it having a pH of 10. Double check your calculations. We may have made a number error. I think when I did this, I got a slightly different answer. Or maybe I got the same answer. I did this a long time ago, so check. But otherwise, this is all completely correct. So I guess the key principles from this question, I threw you on the deep end to teach you this. Whenever you have pKa, what can you find, everyone?
Okay.
Remember that. Never forget that. Okay. Now, the other thing is whenever you're approaching a question, a tough question, always frame the question. Write down mathematically what it is you're trying to find, and then work backwards in what you need to do to get there, right? Just as how we did. Go down multiple pathways and you can start canceling out other ways to get your answer, okay? So that'd be very, very important to do. The other thing is, whenever you have K, so the first principle we learned today was whenever you have pKa, find Ka. Whenever you have Ka, what should you find, everyone?
Kb.
Yeah, you could find Kb if it's the question with two equations. Typically, we'll not be given a Ka, Kb question. So this was a rare type of question. But my logic for you is whenever you have Ka, sure, you can find Kb. That could be another idea in your head. But usually, you will be finding concentrations using a Rice table. That would be your plan of attack. So if you remember these key points here and framing the question, you would have got this entire question correct.